So, today I will do a couple of practice problems. Okay. You should also, in addition to these practice problems, I also encourage you to look at the textbooks suggested for the course to see practice problems in them. In particularly this part is very well discussed in the book by Macquarie. Okay. So, let us pick a couple of practice problems. So, the first one I will read out the problem. Suppose we have a distribution p of x given by 1 by root pi e to the minus x square, and we change variable using y equal to x square. What is p of y? The distribution of y. Okay. So, suppose you have a distribution of one variable and you change the variable, then how do you look at the distribution of the new variable? Okay. Now, this is in order to solve this, you need to think a little bit more about how this transformation of variables and what it does to the probability distribution. Okay. You remember that you always have the condition that integral p of x dx over the range from minus infinity to plus infinity, this should be equal to 1. Okay. And so, what you would expect is that if you change the variable y, then you would also have integral p of y dy for whatever the range of y, this should be equal to 1. Okay, over the range of y, since y is x square, x is so y has to be positive, so it will be 0 to infinity. So, this should be equal to 1. Okay. So, when we make this transformation, you have to satisfy this condition. Okay. So, what we do is we choose a transformation that satisfies p of x dx equal to p of y dy. Okay. So, we choose a transformation that satisfies this, and so what you will get is you can show that this works out to be p of y equal to p of x into dx by dy, and I can write this as p of x divided by dy by dx. Okay. So, what we have is p of y is equal to p of x divided by dy by dx. Now, this equation is actually a little misleading, because what you are supposed to write is, in this equation you are supposed to write x as a function of y. So, I should actually write this as p of x of y. Okay. So, wherever I have x in the expression for p of x, I replace it by y divided by dy by dx, and again dy by dx should be, this should be expressed as a function of y. Okay. So, let us go ahead and do this. So, what you have is y equal to x square, dy by dx is equal to 2x, but this is expressed as a function of x. So, if you want to express this as a function of y, you will get 2 root square root of y, okay, because x is nothing but square root of y. And so, what you will get now, I can write p of y. Okay. So, what I have is 1 over square root of pi, and I have e to the minus x square is nothing but e to the minus y, okay, and then I have to divide this by this derivative. So, it should be into 1 over 2 square root of y. Okay. So, what we had initially was p of x is equal to 1 over square root of pi e to the minus x square, and when we set x square equal to y, in the probability distribution for y, not only does this change, but also there is an additional factor. Okay. So, this problem is a very general problem that shows how you go from distribution of one variable to distribution of another variable. Okay. So, it can be used, it is a general method that can be used to transform from one variable to another. Okay. So, the next problem that I want to do is a more specific problem, and this is related to the Maxwell-Boltzmann distribution of velocity components. Okay, and we will also use some of what we learned from the previous problem here. Okay. So, p of Vx, Vy, Vz is proportional to e to the minus m Vx square plus Vy square plus Vz square divided by 2 kBt. So, what you are asked to do is to normalize this function and calculate the distribution of speed. So, this is a distribution of 3 components. So, it is a multidimensional distribution, it has 3 components, and you convert it to a distribution of a single quantity v, which is given by square root of Vx square plus Vy square plus Vz square, and then you calculate the average speed, most probable speed, and the root mean square average speed of this Maxwell-Boltzmann distribution. Okay. So, again you can do this, it is a very standard exercise when you do kinetic theory of gases. Okay. So, just to show how you will go ahead and do this. So, first let us look at the normalization. So, notice that P of Vx, Vy, Vz, okay, is equal to e to the minus m Vx square by 2 kBt into e to the minus m Vy square by 2 kBt into e to the minus m Vz square by 2 kBt. Okay. So, what we realize is that this distribution factors into 3 distributions, one that depends only on Vx, other that depends only on Vy, and the third that depends only on Vz. So, what can you do with this? Now, your condition is that integral P of Vx, Vy, Vz, no, this is I should write this is proportional to, okay, dVx, dVy, dVz, this should be equal to 1. Okay. Now, what I can do is I can write this, because I see that my this factors into 3 factors, I can write this as integral P of Vx dVx into integral P of Vy dVy into integral of P of Vz dVz, and what I am going to do is going to insist that each of these is equal to 1. I am going to normalize each of these distributions separately. Okay. So, you know the normalization constant for, if you just take one Vx, okay, then you have this is equal to a e to the minus half m Vx square by kBt. Okay. So, what you can say immediately is that you know the value of this normalization constant because this is just a Gaussian function. Okay. So, the normalization constant I can write as square root of this quantity a, which is m divided by 2 kB t, okay, square root of a divided by pi. Okay. So, that is the normalization constant for this, and what you can see is that the same normalization constant will appear will apply for Py and Pz. Okay. And so, what I can do with this whole exercise, I will just complete the writing of this quantity. Okay. So, this is my normalized PVx. Okay. Again we use the idea, we took this a just from a usual Gaussian function. So, if instead of if you had e to the minus a x square, then the normalization constant is square root of a by pi. So, here instead of a you have m by 2 kBt, okay, and so that is what I replaced a by that. Okay. So, now we have the normalization constant for Vx, we can do similarly for Vy and Vz, and so I can write P of Vx, Vy, Vz is equal to m by 2 kBt pi raised to 3 by 2, okay, because I will get half factor from each of them, okay, and I will have e to the minus half m Vx square plus Vy square plus Vz square divided by kBt. Okay. So, this is the normalized Maxwell-Boltzmann distribution of velocities. Okay. Now, the next thing that we wanted to do, if you go back to the problem, is you wanted to calculate the distribution of the speeds P of v. Okay. So, to do this we will just look at this distribution, and then what you want to do here, you have Vx, Vy, Vz, okay, and what you want to calculate is the distribution of the speed v. So, here we have 3 variables and here you have only one variable. Okay. So, actually what you need to do is to, when you look at the expression for v, v is equal to square root of v x square plus v y square plus v z square, okay. And you immediately realize that this is nothing but the length of this velocity vector, okay. And so, you are going from x y z to a length, okay, and that should remind you that what you are doing is actually a transformation of coordinates from x y z to spherical polar coordinates. So, you are going from this to, there should be two other components, one is a theta component and a phi component. Again, these are not important in this description, because you can work it out by normalization, okay. So, when you do this transformation, then the easy way to see what this transformation should be is to insist that you should have p of v x, v y, v z, dv x, dv y, dv z. This should be equal to p of v, v theta and v phi, okay. So, these are the two angular components, I am just calling them v theta and v phi, okay, times Jacobian for this transformation times dv, dv theta, dv phi, okay. So, the way dvx, dvy, dvz that transforms is j times this, and this j for spherical polar coordinates, okay, is actually equal to v square sin v theta dv theta dv phi, okay. And what we notice is that this distribution, this p depends only on Vx, Vy, it depends only on the sum of squares. So, it depends only on V, it is independent of V theta and V phi, okay. So, this independence allows us to write the following expressions. So, you can write this as p of, it depends, it is independent of theta and phi. So, I will write it as p of V times V square and this sin theta, V theta, d theta, d phi, and then you have a dV, okay. So, this whole factor I can just replace by 4 pi, okay, and then I have a dV, okay. So, these are very standard things that you do when you work with curvilinear coordinates or spherical polar coordinates, okay. So, you have a 4 pi v square dV, okay. So, now I can write this as 4 pi v square. Now, p of v is just p of v you can get by looking at the expression for. So, we notice that this whole thing in this whole expression is just equal to v square, okay. So, that allows us to write this as, so you keep the normalization factor as it is. So, you have m divided by 2 pi k b t, this thing raised to 3 by 2, and you have e to the minus half m v square by k b t, okay. So, this is the Maxwell-Boltzmann distribution of speeds dV, okay. And what you can say from this is that p of v, this is equal to, okay, I should call this p prime of v here, because what you are doing is you are expressing the original distribution in terms of Vx, Vy, Vz in terms of v, okay. So, finally, what you will get is you will just identify this whole thing as p of v. So, you will say this is 4 pi v square m by 2 pi k b t raised to 3 by 2 e to the minus half m v square by k b t, okay. So, once you have this, then you can say that what we did is we had a p of Vx, Vy, Vz, and you had dVx, dVy, dVz, and you went to p of v dV, okay. So, this is what gives you the Maxwell-Boltzmann distribution of speeds. So, then this p of v is given by this quantity, okay. Notice that what you have is, you do not have just a Gaussian in this case, you have a Gaussian multiplied by a v square in front, okay. So, this is the very standard Maxwell-Boltzmann distribution of speeds that you have seen in your kinetic theory of gases. Now, the next thing is to calculate the average speed, most probable speed and the root mean square average speed of this Maxwell-Boltzmann distribution. Okay. So, the average speed V is equal to square root of Vx square plus Vy square plus Vz square. Okay. So, this is speed, okay, and average speed is equal to integral V times P of Vx, Vy, Vz dVx, dVy, dVz. Okay, and this is a triple integral actually, because you are integrating over Vx, Vy and Vz. So, I will just write this as a triple integral. Okay, and each of Vx, Vy, Vz go from minus infinity to plus infinity. Okay. So, if you want to calculate the average speed, then what you do is again you do the transformation to spherical polar coordinates, okay, and you can use P of V, okay, and what you will get is, I can write this as 4 pi and then I take the m by 2 pi kBt raised to 3 by 2. So, I am just copying this expression from here. So, I am just taking this expression and bringing this here. Okay. I took all this outside the integral and then I have a single integral from 0 to infinity. So, the speed can only be positive. Okay. So, V goes from 0 to infinity and now I have a V into V square e to the minus mv square by 2 kBt dV. Okay. So, that is essentially the expression that you get, and now you have to evaluate this integral. Okay. Now, this integral goes only from 0 to infinity and you have V cube e to the minus mv square by 2 kBt, okay, and you have to evaluate this integral. Okay. So, this is how you will calculate the average speed. Okay. So, the average speed is given by this expression and we can go ahead and do the calculation. I will just write this in a slightly different form. So, I will take the factor of pi outside. So, I will have a pi raised to 3 by 2. So, I will just write it as 4 divided by the square root of pi. Okay. So, and then what I will write is m by 2 kBt, this raised to 3 by 2, and what I have is integral V cube e to the minus m by 2 kBt V square dV from 0 to infinity. Now, this is actually a standard integral, you can do this using gamma functions, but I will just show you how to do it explicitly. Okay. So, I will just show how to do this integral explicitly. So, what we will do is we will put V square equal to t, okay, then 2 V dV equal to dt, okay, and so what I can write this. So, I will get 2 by root pi and I have m by 2 kBt raised to 3 by 2, and what I have is integral 0 to infinity. Now, I have t e to the minus t into the factor of m divided by 2 kBt and I have dt. So, this is what the expression looks like, and now you can do this integral, integrate by parts. Okay. So, when you integrate this by parts, you will get two terms. The first term will be t times the value of this integral, okay, and the value of this integral is just exponential divided by a constant, and basically you have t times e to the minus. So, I will just write this factor as it is, I will not write it out again, okay, but what I will have is two terms. The first term will be t e to the minus T m by 2 kBt divided by minus m by 2 kBt, okay, and this has to be evaluated from 0 at the boundaries 0 and infinity, and the other term will look like integral will look like so minus minus it will become plus 2 kBt by m, and I have integral e to the minus T m by 2 kBt dt from 0 to infinity. So, these are the two terms you have, and instantly you realize that this term when t equal to infinity, e to the minus infinity goes to 0 much faster than t goes to infinity. So, this product goes to 0 at infinity, it goes to 0 at when t equal to 0, this term goes to 0. So, this term is equal to 0. The second term, okay, will just have this times this integral. So, the factor of 2 kBt by m times this e to the minus T m by 2 kBt, you can easily do this integral, okay, and what that will do is it will give you an additional factor of 2 kBt by m. Okay. So, what this will give is so I will just write it out right now. So, 2 by root pi, and I have m by 2 kBt raised to 3 by 2, and I have 2 kBt by m square whole square, and then what I have is so the second square came from doing this integral, and I have e to the minus T m by 2 kBt, okay, but there was a minus sign. So, the limits are actually infinity to 0. Okay. When t equal to 0, this is equal to 1, when t equal to infinity, this is equal to 0. So, this is just 1. Okay. So, finally, what I can write this as, so I have 2, so I can write this as 2 by root pi into 2 kBt by m raised to half. So, if I want to take this 2 inside, I have to square this. So, 2 square is 4, 4 into 2, I can write this as 8 kBt divided by pi m raised to half. So, this is the expression for the average speed. So, this is a standard expression that you have seen in lot of the books, and we saw how you can get this from the Maxwell-Boltzmann distribution. Now, what about the other speeds that you were asked to calculate? You were asked to calculate the most probable speed and the root mean square speed. Okay. So, the root mean square average speed is actually again fairly easy to calculate. So, the v root mean square, okay, so this is defined as the, so I can say the v square root mean square is the average of v square. So, you take the average of v square, okay, then you will get v root mean square, the square of that, okay, or you can write v root mean square is the, or I have been using the slightly different notation for average. So, I will just stick to that and use our notation. So, it is the average of v square, okay, or you can write v root mean square as the square root of average of v square. Okay. So, essentially what you need to do is you need to calculate the average of v square. Okay. So, this is nothing but the average of Vx square plus Vy square plus Vz square. Okay. This I can write as average of Vx square plus average of Vy square plus average of Vz square. Okay. And now if you look at the Maxwell-Boltzmann distribution, the 3 directions are identical. So, the 3, if you look at the Maxwell-Boltzmann distribution of velocities, so there is nothing that distinguishes x, y and z. In fact, whatever you get for Vx square, you will get the same for average of Vy square, and you will get the same for average of Vz square. So, I can go ahead and I can calculate Vx square average. Okay. So, I can calculate this. So, now this is only a function of x. So, I can write this as integral from minus infinity to plus infinity Vx square times p of Vx dVx, okay, and this you can show this again using the integrals that we have seen. So you write this as minus infinity to plus infinity. Now you have V x square. Okay, now P of V x, what we said that was equal to m by 2 pi k b t raised to half. Okay, the half because you are looking only at V x, and e to the minus m V x square by 2 k b t dVx. So, this is the average of V x square, and you can show that this is equal to, when you do this integral, you will get this equal to k b t by m. So, all the other factors will go off, and what you will be left with is k b t by m. Okay. And you can similarly show that this is equal to V y square average, and this is equal to V z square average. Okay. So, this part it takes a little bit of work to show, but it is not very difficult. Okay. So, then you can write V square average is nothing but k b t by m plus k b t by m plus k b t by m equal to 3 k b t by m. Okay. Or V r m s is equal to square root of 3 k b t by m. Okay. So, this tells you what V r m s is. Now, what about V most probable? So, V most probable so this implies P of V is maximum. Okay. So, where is P of V maximum? So, P of V we wrote as 4 pi into m by 2 pi k b t raised to 3 by 2, and you had V square e to the minus m V square by 2 k b t. Okay. And so, if this is maximum, means the derivative of this with respect to V should be 0. So, dP of V by dV at V equal to V most probable equal to 0. Okay. And so you have to take the derivative of this quantity, and this if you work out, you will get V most probable equal to 2 k b t by m under root of that. Okay. You have to work this out, and you will get this result. Okay. So, so with this I conclude this practice problem, and in the next class we will go to the second module. Thank you.